In this short video, we are going to try and understand the concept of time to live, TTL. So, whenever you have a source and a target device that are connected across the internet, any data that is exchanged between these two devices happens in the form of IP datagrams. So, the source device sends out IP datagrams to the target, and the target in turn also responds with IP datagrams. So these two devices, the source and target, are connected via intermediate routers. Now, when an IP datagram starts from the source device towards the target, right, it naturally reaches the directly connected first router, which then forwards the IP datagram to the next router, the second one, and then which naturally forwards it to the third router, and so on until it gets to the target. After which the target device replies by sending one or more IP datagrams back to the source device, which once again pass through all the intermediate routers. So this process of an IP datagram starting from one device and getting to another device, routers included. So this is called hopping. So for example, from the source device, the IP datagram reaches the directly connected router, that's one hop. Then from there, the next router, that's another hop, and so on. An IP datagram consists of the IP header and the payload. So this TTL field is found inside the IP header. Now if it's IPv4, then it's just called TTL. If it is IPv6, then it is called the hop count field. Two different terms, but ultimately the concept is the same. Now, on the source device, whichever operating system is running, so it is the responsibility of that operating system to make sure that the TTL value is set for every IP datagram that is being sent out from the source device towards the target. Because it is this value that decides how many intermediate routers or intermediate devices ultimately that an IP datagram can pass through as it makes its way from the source device towards the target. Call it the maximum number of hops permitted for an IP datagram. As an IP datagram starts out from the source device towards the target device, assume the operating system on the source device set the value of TTL for that IP datagram to 64 and forwarded it to the directly connected first router, right? So this first router is now going to examine the TTL value, see that it is 64, decremented by 1, so it becomes 63, write the 63 back into the TTL field of the IP datagram itself, thereby modifying this IP datagram. And then this modified IP datagram gets forwarded to the next router down the line, which then repeats the same process. So the 63 becomes 62 now, and the modified IP datagram keeps getting forwarded towards the target. So as you can see that the closer the IP datagram gets towards the target, or at least moves towards the target, you can imagine that the TTL value keeps decreasing. Now it is entirely possible that before the IP datagram reaches the target device, the TTL drops down to 0 at some router along the path, right? So if the TTL value drops to 0 at a certain router, it is the router's immediate responsibility to discard this IP datagram right away and send back an ICMP time exceeded status response back to the source device. Now, why is this TTL mechanism needed at all? So, on the internet, there may be thousands of millions of routers. So, given a source and a target device across the internet, we don't know how many routers might lie along the path between these two. So, the point is that the TTL aims to set a maximum limit on the number of routers through which an IP datagram can pass as it gets towards the target, right? That is the number of hops. So we don't obviously want an IP datagram to be circulating infinitely across the internet to all these routers. Okay, you go from here to there, from there to somewhere else, like what you might have experienced in our government departments or the municipality, for example, right? So that kind of reduces the efficiency and defeats the purpose of the internet itself. So to prevent this from happening, you have a limit that is set, and the IP datagram is killed if that limit is exceeded. Okay, so from this flowchart, we are going to try and understand how IP datagrams are processed by a router but strictly from the TTL point of view. Okay, let's start from here. So an IP datagram arrives in the router's queue and it picks it up for further processing. It looks at the IP header. Then the very first question that is to be asked here is this router the target device? See, the source device had sent out the IP datagram to reach the target. Now the IP datagram has arrived here on this device. Now this could be a desktop, it could be a server, it could be a router, whatever this device is. So is this the target device? If yes, then process that IP datagram right away and reply appropriately. But no, if this device is not the target, then decrease the TTL by 1. So now the next question is, after reducing the TTL by 1, did it become 0? If it did not become 0, then in that case, take this reduced value of TTL and overwrite it back into the TTL field of the IP header of this IP datagram, right? Once this is done, just forward it, forward this modified IP datagram with that reduced TTL value to the next router. But yes, the TTL became 0 after reducing it by 1, then in that case, delete this, discard this IP datagram right away, don't process it any further, don't forward it any further, and immediately send back an ICMP time exceeded status message back to the source device. Hope that was clear. Okay, so lastly, let's try to understand this diagram and wrap up this discussion here. So the theoretical maximum for TTL is 255. Linux, Mac, and Android set it to 64. They are all ultimately Linux variants. Windows, however, sets it to 128. All right, so let's try to understand the various elements that are in this diagram here. Okay, so starting with the source on the left, right here, the target on the other side, and we have all these intermediate routers, including these three routers through which the IP datagram will pass to get to the target. So if the source device sets the value of TTL as 1 for an IP datagram and forwards it to the first router, it will naturally get discarded at that router itself. Question is why? Well, you remember that we had this flowchart previously, right? So let's try to look at the behavior of the router from this flowchart. So the IP datagram just arrived in the queue, right? So the router is going to look at the IP header. Is it the target? No, of course not. So decrement the TTL by 1. But remember, TTL itself was 1 when the IP datagram arrived. So naturally the TTL is going to become 0. And if the TTL becomes 0, then the immediate responsibility of the router, discard the IP datagram right away and send an ICMP time exceeded message back to the source device. So if the source device sends out an IP datagram with TTL2, now go back to the flowchart, you know that it's going to die at the second router, get discarded at the second router. So similarly, TTL3 gets discarded at the third router. So you can see that to reach the target device, we need at least the TTL to be 4. Now let's go back to the previous point that we discussed. Linux, Mac, and Android set the TTL limit as 64 and Windows sets it at 128. Now what that means is across the entire span of the internet, including all the devices that are connected to it, they may be servers, routers, whatever, all kinds of intermediate devices as well. So what I'm trying to say here is that between the source device and the target device, there can only be a maximum of 64 routers, because see the between the three numbers here, the theoretical maximum of 255 and 128 for Windows, and then 64, the minimum number is 64, right? So let's go with that number. So that means that you can only have a maximum of 64 routers between the source and target device.